So let's go to the next topic. And this is going to be even more exciting. 2.2.4, circuits that cause POP to fail. So let's click on that topic. Let's do our cleanup and make sure you don't save, because you want to save all the hand scratching that I just did. Okay, so we're going to look at more ways that we can make POP fail and how to figure out what we did wrong and fix it. Okay, so let's look at, we'll go back to the file view and we'll go to schematic 2.9. Hit the home key and let's run this. Okay, we had a failure. Now notice the error message is in the command shell. That same error message shows up down here in the health report. So it says, we went to the maximum period. There was no switching action. What should we do? Well, let's go. So now we have the same circuit as we had just a second ago, but now we're hooked up to the clock. And, so we've got our threshold 2.5. That all looks good. So what's the problem? Well, let's look and see what this ramp generator is. So
only 1 volt.
It's only 1 volt. So now we could change.
Well, you could just hook up to the comparator.
You could hook up to the comparator. Then if we had a real feedback loop, we would have the issue that sometimes the controller can get in a state where it tells the switching to stop. Here, we don't have that problem. So we know the threshold over here is 2.5, so we could make this 5 volts. But now we're changing the gain of the system. That's probably not a good move, right? So what can I do? I can come over here and just change this threshold to 0.5. So let's do that. We'll change the threshold to 0.5 and give this another go. Okay, so that looks like we had glorious success. Okay. So again, we had that same error. We hit the maximum period, didn't see any switching. Now we just have to figure out, well, why is that? So typically you want to make sure your threshold is right and it's compatible with what's going on here. Okay. Okay. All right. So let's do the next one. So let's close the circuit. Close, that schematic. We'll get rid of that error message. And we're going to go to schematic 2.10. So 2.10. Okay. Hit the home button. Okay. So one thing, so we're driving, so we can look at the SR latch and we can see that its output high is 5 volts. And we can see that the trigger is 2.5 volts. So let's give this a go. Okay. And what's the error message? Same thing. It's looking at the output of the POP trigger and it's not finding anything. But check this out. It's suggesting you might want to check the input pin of the POP trigger. Make sure it's correctly attached. So let's go back and look at that. This is actually, a slightly modified version of a tech support question we got years and years ago. Anybody see the problem?
Well,
Yeah, you have the output
of the POP.
Right. So this is everything was done right. He just stubbed his toe at the very last second. So if we disconnect that, and then I'm going to mirror it and hook it back up. And let's give that a go.
Yeah, glass of this one usually can lead to this, yeah.
Yeah. The problem is, it looks so right. It's just not right. And so, yeah, so now everything's good. We got steady state. Everybody's happy. Okay, so we can close that out, close out the schematic, note save it, close out the error message. And let's go to the next one. All right, the next one, this is very, well, it's common. It happens often. And if you're making models, you really want to be aware of this. So let's go to schematic 2.11. So here we have a real simple schematic, 1 megahertz square wave driving, an RC. We have a 600 kilohertz square wave driving an RC. And we have the pop trigger is connected to the 600 kilohertz. Okay. So let's run this, see how it goes. All right. So did we succeed? Answer, no. Okay. So let's just look at the waveforms. So let's see. Here's the 1 megahertz signal. Here's the capacitor that's being driven by the 1 megahertz signal. Here's the 600 kilohertz signal, square wave. Here's the capacitor voltage being driven by that. And then here's the output. The X1 out is the output of the pop trigger. Okay. So you can see we're triggering off of the 600 kilohertz. So the problem wasn't that we got to the maximum period and it didn't, there was no switching, plenty of switching, but we did 20 passes through the core pop process and didn't succeed. Now in the Elements version, this doesn't work, but in the full version, it does. What it's telling us is C2 is the energy storage element that is causing the largest error. So you might want to check that out. So in the full version, if I click on C2 and come back to my schematic, this would be highlighted. And when you have a big, hairy schematic, particularly like in our case, we get a big old schematic from somebody asking, with some tech support question, where in the world is, it's like, where is Waldo? Who knows where that is? This kind of helps you find it. But, so what's the problem? All right. So there's one other thing we can look at, and so when I see this, I like to look at my stethoscope, my status window, and let's just take a look at this. So the error is 16%, 3%, 13%, 16%, 3%, 13%. So it's just banging its head against this wall, and the error is really large, way far away from our convergence criteria. And it's real obvious that saying, okay, well, maybe 20 passes isn't enough. Going to 100 passes isn't going to change this. This is just, it's getting nowhere fast. Okay. This signature, it's like you put the stethoscope on, you listen, say, okay, breathe, take deep breath for me. When you see this signature, it's very common for this problem. So what's our issue here? What is the issue? This is our pop trigger. If we look at, so we're looking at how many energy storage elements we have. We have 2. And if we look at the pop trigger and say over here, and we look at the 600 kilohertz, we can see that, okay, this value at the capacitor at the beginning of one cycle and the beginning of the next pop cycle, that actually looks like it's converging. That's going to work. But if we look at the same moment, at the value for the capacitor at the 1 megahertz at the beginning of one cycle, and then 1 megahertz at the beginning of the next, they're quite different. They're quite different. And so because these frequencies are just not related to each other, pop's is not going to succeed. Okay. So This is actually quite common, particularly when you have big complicated circuits. It's real easy to say, well, I got this one function over here and it's just minding its own business. My power supply is over here running at 600 kilohertz, doing its thing. But if there's any energy storage elements associated with what's going on here, it could cause POP to fail. So, there's lots of ways to deal with that, but one level of your model might be, let's disable this stuff because it doesn't have anything to do with the power supply. And what we're trying to do now is to get the power supply in steady state, so we can do some analysis on it. So let's, have an option that will allow us to disable this activity.
Just additional comment. If you have somewhere a capacitor that's not even switched, but it's initialized and it has a bleeding resistor on it, you run into the same problem because that voltage changes gradually and the error is essentially there at the beginning where it's largest and it will fail.
Right. So if you had an initial condition on this resistor, and let's say on this capacitor, and this was just connected to ground, so during the simulation it's just discharging slowly. Yeah, that would do the same thing. You're right. That would do the same thing. Now it might be that POP would be able to figure out, well, this is eventually going to get to zero and we're okay. But if there's any signal associated with this that's not related to what's going on here, it's going to likely be a problem.
Also, if you have a design that's basically a battery charger, if you don't design the battery model correctly and the battery voltage is slowly charging during POP, it's a gigantic, it looks like a gigantic capacitor, so effectively POP will never succeed that way.
Yes.
So you have to design your battery model so that during AC, a POP AC, you basically switch a voltage across the cap with a voltage source and switch the cap out of the circuit and operate like you're a constant voltage so that it's not changing during POP. And then during transient analysis, if you want to look at charging, you switch back. So at T0 transient analysis, you switch the capacitor back in.
I had never thought about that, but you're absolutely right. You're absolutely right.
We have done that for some models for IC chargers before, Tom.
Yep. Okay. Another case where you can run into this in a bigger is, let's suppose I have two power stages and they're operating at they're not synchronized to operate at the same frequency. So this isn't just an RC, but it's a whole power supply, and this is a power supply, and they're connected somehow, and I want to see if the whole system's stable. Then that becomes yet another challenge. And so let's just let's take the next step here with this example, and that'll shed some light on things. All right, so how do we fix this? Well, you might notice there's this little block here called and it's a divide by 3 block. And so this is 600 kilohertz, and we divide by 3, and this terminal connects to this node, and so this is a 200 kilohertz signal. So I'm going to double click on my jumper, and watch carefully here. We don't want to do anything over here. We just want to go from position 2 to position 1, okay? And then click OK. And so now my jumper is connected such that my POP trigger is connected to the output of this divide by 3, so it's connected to a 200 kilohertz source. So now the question is, how's this going to work? Okay, so let's take a look at that. And that would appear to be glorious success. Okay, so now my output trigger is connected to this 200 kilohertz source. All right, so for every one POP interval, POP cycle, I have 3 600 kilohertz cycles and 5 1 megahertz cycles. And so it turns out that, now if I look at the capacitor voltages at the beginning of each 200 kilohertz cycle, both my values on C2 and my values on C1 are the same each cycle. Okay, so now POP can succeed. So now if we go back to that analogy where this is one power supply, this is another power supply, if I can sync these somehow, and even if they're not the exact same frequency, if I can sync them so that one is a integral multiple or they have a common multiple, and I can do some kind of divide by scheme, then we can make that work. Okay, so we've done that, we've done that. All right, now let's do this. Last thing on this one. Let's get rid of C2. So let's delete C2. And now ask yourself, is this going to work? All right, so the other thing is I'm going to put the jumper back to position 2. All right, so now I'm going to trigger off of the 600 kilohertz signal again. Okay, and it didn't work before because I had 1 megahertz, my 600 megahertz. They're not related to each other, and they're not going to synchronize on a 600 kilohertz pop trigger. But is this going to work? So let's take a look. So ask yourself, mentally make your note. Okay, and sure enough, it does. Now, why is that? So let me ask our roundtable, why is it work? The same thing that did not work before is working now.
You got lucky that the voltages, when you checked them, agree.
There's only one storage element in the circuit.
Right. Remember, POP only is looking at energy storage elements. It's not looking at the waveforms everywhere else. It's only looking at the energy storage elements. And there is no energy storage element now that's impacted by the 1 megahertz signal. So it's not that I can't have other frequencies flying about. It's just that they can't impact energy storage elements. Okay, so now, now everything's fine because there's only one energy storage element that is being, switched, and it's being switched by the 600 kilohertz signal. So everybody's good, everybody's happy. Okay. So this is really important, and this is not uncommon. And if you're building a controller model, you always want to keep this in mind, because you can hurt yourself by building things and not realizing that, okay, if I have energy storage elements that are operating at different frequencies that are not related, they're not synchronized, you're going to defeat POP. All right, so you need to have a way of dealing with that, and you want to build in that way of dealing with that, right from the beginning. Okay. The other thing to remember is that you have this very distinctive, signature in the errors of, all the different passes from the core POP process. They tend to flatten out at a number that's quite far away, usually quite far away from the tolerance, the convergence criteria for POP. Okay, so this, and we're going to look at one more example where we can kind of see this. Okay, but this is something that you need to be aware of, and you want to think about. And if you're designing controllers, you want to take that into account as a first order consideration on your design. Okay. All right. Yes, sir.
I'm not sure I heard, but did you mention anything at all about KVL errors? I think for new users, maybe just a very brief mention of violation of KVL.
Ron, do you want to speak to that?
We haven't prepared our course for the violation of KVL and KCL. That's interesting. Okay. So maybe we should include a little bit mention about that in our course in the future. Basically, violation of KVL and KCL happen when you assign inconsistent initial conditions. And a very simple example would be if you put two capacitors in parallel, pure capacitors, no ESR, no ESL, and you put two of them in parallel, and you specify one to have initial voltage of 5 volt, and the other one initialized to 3 volt. Then you get a KVL violation error, because going around a loop, we find out that the voltage going around the loop once does not add up to 0. So that's a violation of KVL. So it's more challenging when the circuit is more complicated and you have a lot of LCCs. But that basically suggests that it is due to inconsistent assignment of initial conditions.
Right. So that's one of the, and we'll talk about that very soon, actually.
Do we? I never thought that.
I have a special topic on that. Not KVL, but it's kind of it results. It's how to initialize circuits. Okay. So we'll do that right after this topic, actually. Okay. So in your docs, we have a really good example, an LLC converter example. You'll need the full version to run that because that circuit's quite large, but it has an example of what happens when the switching stops. And it's a quite interesting and good example, and shows you how to address some of those issues. All right. We're going to do one more example, and then we're going to talk about how to initialize schematics so that they will pop quickly. Okay, so let's do one last test schematic. So first we'll tidy up, close our schematic, don't save. We'll get rid of the error message. We'll close up the waveform viewer. So now let's go to schematic 2.13. Okay. So now what we have, again, it's the same circuit that we had before, but now we have we've injected a sine wave. So we've injected some noise in the system. So here's the reference voltage, and now we put some noise on top of the reference. Okay. And it's not a lot of noise. It's a, 20 picovolt peak to peak noise signal. Okay. And the frequency, notice the frequency is 250 kilohertz. Our switching frequency is 500 kilohertz. So if we run this, let's look. So again, we see the LC are the two. So it's the output inductor and capacitor that are creating the largest errors. If we go back to our schematic, we see it's these two parts. Okay. But let's look at the signature of the status window here. Here we can see, look at this. It's still got that flat thing, but now the errors are small. It gets down to 10 to the minus 10, 10 to the minus 9, but it can't get better. So it's right on the edge. And we did this on purpose. We figured out what's the largest peak-to-peak signal we can put in that will cause it to fail, cause the circuit to fail with the convergence criteria we have. So we're injecting a signal that's not synchronized with 500 kilohertz. And it's just large enough so that it causes Simplest to not be able to meet the convergence criteria for pop. Okay. So this is where you can see, okay, we're almost there, but something's going on that we just can't quite get there. Now, how would you fix this? Well, you could go in here and change the convergence criteria. That's a possibility. It might work, but maybe it's not the best idea. Okay. But let's talk about a more robust solution than caving on that. It may be that there's just enough, whatever reason, noise in the system, you have to do that. But in this case, that's not the case. All right. So we can make the noise smaller, but there's another thing. Notice this is 250 kilohertz, exactly half. Because this happens so often, we have a divide by two box. And in the LLC converter, you'll see that we have that. And we have, this gets used quite often. If you have a push-pull converter, almost always the clock is twice the frequency of the actual conversion frequency of the power supply. And so clocks are good places to trigger for POP, but you need to have this divide by 2 capability. We can use the divide by 2 in this case to address the issue that the noise that we're injecting happens to be half the switching frequency. So if we do our POP trigger on 250 kilohertz, then the system, is stable. Another thing that's kind of fun to do with this circuit, I'd encourage you to maybe play with it, is, well, how about if we just reduce the level of noise? What happens then? Okay, so if I go down to plus and minus 1 pico, then it works. It'll be interesting to see what so here, our signature is now it's just enough better that we can converge. It's not 10 to the minus 12, 10 to the minus 13, but it's enough better to, to meet our convergence criteria. Okay, but this flat thing is indication that there's some signal that is not quite in sync with the conversion frequency of the power supply, and it's injecting noise in the system. So how can you address that? So there's a couple things. One is to either reduce get rid of the noise source, and that's what we did previously, but we said, okay, we just have to disable that part of the circuit, or maybe we do the divide by 2 scheme. Okay. All right. Any questions on any of that? Okay. All right. So Chris, you might, be getting, preparing yourself, because we'll take a break once we finish the next little topic, which is initializing converters. You'll be up next. So just a quick review. There's quite a few things that we have to, make sure are correctly adjusted, thresholds, the POP trigger being compatible with the source it's connected to, making sure that we don't have multiple independent frequencies that are connected in such a way to disable POP. And we need to make sure it's connected to the appropriate periodic source. And if the circuits are unstable, POP just is not going to succeed. All right. And we kind of can simulate this unstable. Like, for example, if you made this a different frequency, so you can play around with this circuit. It's quite interesting and informative. Okay. So now what I want to do is let's tidy up here. And I want to go to schematic 2.7 AE. Hit our home key. And we just want to look at the circuit. So I'm just going to blow up. We're not going to actually need to run it. And the other thing that I want you to do is you could go down here, right click and open containing folder, and scroll to the bottom if you're, depending on how you're organized. But we want to find this Word document called Guidelines for Initializing Simplest Power Supply Schematics, and double click on that. So we have 2 different kind of cases that I want to look at here. So we talked about the scheme earlier about using the .include statement. So I have .include in the path to go to my .init file. Okay. And what that does is it places that file, the contents of that file, it gets placed after you hit the run simulation. Before the simulation simplest actually gets invoked, we put all the information of the .init file into the F11 window. Okay. This technique is outstanding for when I want to check out a brand new model and see if it's behaving properly. And as we did in our exercise, we could kind of walk through a soft start transient, just kind of incrementally daisy chain our way along and check out the behavior a little bit at a time, but then look at the next period, then the next time period, and so forth. Okay, so it works great for that. One thing you'll notice is when we do that, every simulation starts from t = 0. So it's not like if we were using the snapshots, but it's very easy. You don't have to, you just have to hit go and then go and then go. Because when we use the path name, which is going to that simplest data directory, this file is getting overwritten every time we complete a simulation. So then when I run the schematic again, I'm running it with the updated .NET file. Okay, so really, really helpful. When I finally get to a .NET file that I like, okay, this is a keeper. I want to use this again tomorrow, the next day, whatever. Then you want to save this .NET file and put it somewhere else, not in the simplest data directory, and give it a unique name. So you can go, you remind yourself what it is, and then you go back and use that when you need it. It's really good for pretty much completely initializing a complex circuit into something that's very close, if not at steady state. Okay, so when you're trying to get POP to succeed for the first time, as we mentioned earlier, you can run along transient, then use that .NET to launch a POP analysis, use that .NET to run POP again, and now you can save, after that POP run, you can save the .NET, and that is going to put you basically right into steady state under those line and load conditions. Okay. We do this all the time in our design verification module test plants. We'll run through and do all the corner cases, nominal case, save a .NET file for all of those conditions. And then as we go through different tests, we'll pull the right .NET file and use that. And that just saves lots of time. The other place where it's helpful is I'm using the same, if I am reusing the same .NET file, the same initial conditions, and doing different analyses from that same starting point. Okay. The technique is less beneficial when you're doing a multi-step analysis that covers a wide range of input and output operating points. So if I'm sweeping the input voltage or sweeping the output load or doing both, good initial conditions for one operating point can be kind of far away from the steady state conditions for the other opposite corner. So high line full load and then low line light load, those initial conditions can actually be quite far apart. So when you're doing a multi-step or you're doing a Monte Carlo, we're just randomly changing everything using .NET, the results of one Monte Carlo analysis to initialize the next Monte Carlo analysis can be somewhat problematic. It can get you into, it can cause some things to fail that don't need to fail, shall we say. All right, so the other place is you're creating an application schematic that's going to be used by multiple customers, and they have a wide range of operating conditions, right? So in these cases, it'd be nice if we had a different approach. And that different approach is what I call, let me selectively initialize the critical few, okay? That is actually a very powerful way to do things. And that's what we've done here in almost all of our training schematics. We've initialized the critical few. Okay. So let's just see what that would look like. So what constitutes the critical few? What we want to do is select those energy storage elements where I can give a initial condition that's going to be pretty much close. For instance, like the output voltage. that's not going to change much between your load conditions. So I want to initialize my output capacitors to be real close to steady state. Okay. So the other way of looking at what is it that I want to initialize? I want to initialize energy storage elements that are associated with very long time constants. Okay. So big output capacitors, definitely. And you may have multiple outputs, so you got to remember to do all of them. Okay. Soft start capacitors are by definition meant to have really long time constants when you think of a switching cycle as kind of your measurement. So you want to create your soft start circuit so that you can initialize it. And we have a nice little webinar on that technique. But soft start capacitors, output capacitors, also capacitors that are providing an integration function around an error amplifier. So even though these are small capacitors, they're always associated with very high impedance nodes. So they are a part of a long time constant. Otherwise, they wouldn't do the integration function, right? So these turn out to be almost the toughest ones to initialize, correctly, because there can often be, your output voltage doesn't change much between high line, low line, and full load, no load. But these in your error amp, these can change quite a lot. So coming up with a good initial value for these can be very helpful. All right. And if we just look at the output capacitor, and if you'll notice, there's a place to put the initial condition. There's also a place to put whether or not you're going to use the initial condition or not. So you have to check that box and put something here. One way that you can really improve your placing of initial conditions, particularly if I have a schematic that, hey, if I configure this differently, the output voltage is going to be, it's not going to be 5 volts, it's going to be 2.5, all right? You can handle that by just parameterizing the initial conditions, which is what we're showing here, all right? The initial condition is, equal to V out. So this is often a really helpful way. You need to think about things more, but I've also used that to good advantage in the capacitors around my error amp. By looking at the I load, I could basically run this to steady state in the four corners, and I could come up with an expression based on I load that would give me a pretty good, allow me to come up with a little expression for this initial condition that would put me in a good place and allow pop to converge quite quickly. Okay. And so the notion of parameterizing your initial conditions can be very powerful. Also, there's a whole bunch of parts that for this application, you're just better off not initializing at all. Okay. And which are those? Input capacitors. Now, this is where Ron and Chris were talking about, if I had a pure capacitor for the input, which typically you wouldn't in a real schematic, but you might, and it's initialized to 1 voltage. But I'm going to use this in a schematic where I'm doing a multi-step and I'm going to change my input voltage. You don't want to have initial conditions on an input capacitor. What you want to do with the input capacitor is you would uncheck this box. All right, don't use an initial condition. Let Simplest figure out what it should be. What are other ones? Snubber capacitors, bootstrap capacitors. Like a snubber capacitor, and in this case, this positive feedback capacitor that is, driving the gate signal based on the secondary winding. Anything that sorts itself out within a few switching cycles, you typically don't want to initialize. Okay. Output filter inductors. So here we have an LC. We don't need to have that be initialized. If that's treated as a short circuit, simplest, whatever the initial load is going to be, it'll get initialized all by itself. Simplest will take care of that quite nicely. The other thing is don't over initialize stuff. So if you have two capacitors in parallel, I just pick the biggest one and initialize that and leave the other one open. Now I'm sure in this case we didn't do that. We didn't follow our own rule here, but that any kind of time you have parallel energy storage elements, parallel capacitors, initialize the largest one and leave the others uninitialized. Inductors, I try my best not to initialize it, and I only initialize it if needs be, and then I'll do a parameterized, say like if I have in a sync buck, or here, if I had to initialize this, a short circuit wouldn't be good. In a buck, often, if this is a short circuit, in your initial condition as your switch is on, then you just switched right into your output capacitor. That's not what you want. So then initializing the inductor to be equal to your load current can get you close, pretty close, all right? But basically spending time with your circuit, figuring out how to get a good set of initial conditions for the critical few will save you loads and loads of time. It's totally worth it. And you can, given that now you know how everything works, how POP works, how the initial conditions work, and that sort of, it will really, if it takes you an hour to get good at initializing your circuit, you're going to save yourself 20, 30 hours in the course of your project. So it's totally worth it. Any thoughts, comments?
Yeah, one thing I would also mention too is I found that so long as you're using the capacitors that have ESR at least in them, it's better to use those than a pure capacitor, even in small signal areas, because I find that simplest POP can succeed if it has some series elements, and it can also help you if you have differing ripple currents in parallel capacitors. Like say, for example, you have one cap that's 1 microfarad, and you necessarily have to have some other one that's 100 nano because it's part of a PDN network or something like that. The fact that there is resistance there allows simplest to more easily find the right answer than if you were to leave them as pure parts.
Right. And then if you have a conflict, simplest can resolve that because you've got that impedance in between.
Right. In general, simplest prefer parameters that are closer to your actual physical behavior. So just like the dial Tom mentioned earlier about the ideal dial, if your off resistance is ridiculously high, on resistance ridiculously low, that's going to cause numerical problem. But when you give them reasonable values that are proportional, appropriate for your circuit, then it will work better. So same thing for the ESR and so on. I would like to add 2 comments on the initial condition. When you say bootstrap capacitor, which kind of bootstrap are you talking about?
Okay, so what I'm talking about there, and I don't have a good scoop, but it's when in a sync buck where you have a bootstrap capacitor that
for the high side FET,
it's providing a bias for the high side FET.
Right. Okay.
Yeah.
I would add a comment that yes, normally you leave it open, but depends on how the high side FET gate drive is modeled inside the controller. I have seen circuit where you definitely have to place initial condition on the bootstrap capacitor. Otherwise, that drive circuit could be modeled such that you would go into oscillation without the bootstrap capacitor initialized.
Right. Yeah.
And then the last item is very important, I think, for inductors. What Tom said that if you need to initialize it especially for a sync buck, you initialize the inductor equal to its initial condition equal to the low current, or the sum of all the inductors current equal to low current. We have seen a lot of users tend to say, okay, the output load is 500 amps, so they put a low 500 amp, but if you at that time, if you don't put initial condition for the inductor for the inductors, then what happens is that at T equals 0, right away, you have 500 amp being drawn from the output capacitors. And the current through the inductor as solved by simplest for the initial condition, since we didn't specify it, may not be equal to 500 amp at all. It may be small, it may be large. Most likely it's up to 500 amp, or maybe small if the internal model of the controller is turning off that particular phase. So what happened is that right at T equals 0, you have a big imbalance between the current through the inductor and the low current. As a result, the output voltage would drop until finally the controller model corrected. So if you model a low as a significant current low, you definitely need to initialize the inductor current with some reasonable values. You don't have to be exactly matched, but it has to be some reasonable values so that at T equals 0, the output voltage will not drop tremendously. If it does drop tremendously, what happens is that it will take a longer time for POP to succeed.
Right.
Or your transient analysis may take a longer time to settle.
Right. Yeah. So what you're trying to avoid is having your initial conditions insert or inject a big disturbance, a transient disturbance that's actually not real. It's only there because of the the initial.
Because you set the low to 500 amp at T equals 0 right away. So which is, if you don't have the current through the inductor matching it, that's not realistic.
Right. Right. So it's a thoughtful process, but the return on investment for thinking this through carefully is totally worth it. It's totally worth it. Okay. So I think we are going to now take a 5-minute break, and then we're going to come back, and Chris Swartz is going to share with us some of the things, his experience was using Simplest in system level design applications.